Hello everyone, it's July 26th. Alright, I don't have the gun to go through the solution from the tough problem from yesterday. So the plan today will be finish the challenge here, and after that we're going to just handle an easy problem just to move forward. That will be today's plan. Okay, so this is to flatten a binary tree to linked list. Given a root, flatten the tree into a linked list. The same tree node class where the right pointer points to the next node, okay? Left is always no. The linked list should be in the same order as a pre-order traversal. The heck is a pre-order? I think it's root, left, right. Root, left, right. So 1, 2, 3, 4, 5, and a 6, okay? And we want to put it on the right subtree. So if it's a pre-order, so it will be root and then order left and then right. So we can say on the left, I can flatten this, right? So we call left, and we'll return a root, which is all flattened, and then make this one no. Put this right to here, and we have to return the last. Oof, we need to return two things. Return the root. Actually, we don't have to return the root because I already have it. It's going to be pointing this way, right? So we pointing this way, and we just return the last node of this thing. I return the last node. I return here, I have the last node. The first node is going to be this, so I just cut it. Actually, I don't even have to cut it. I then just call this. Call the right. Oh, I call the right, and then I have to return that. Okay, not sure, but let's try this. Do not return anything. Oh, in place. Okay, doesn't matter. So what I'm gonna do is we're gonna call a function, right? I'm gonna call def helper. When I'm passing a node, and we're gonna return a tree node, which is the last. So what we're gonna do is if node, right? Then we're gonna say node.left. We can call helper node.left. Right, so this one gonna be last left. It's gonna be this. Now after we get the last left, we're gonna say put it at a temp. And then we do that. So we got the last right. So we say last right, helper node.right. Actually, if not node, I'll just return none. I like this pattern better. Okay, so we have the last left and the last right. And then we say temp equals node.right. Okay. Last left or right equals, actually I can just go last equals node.right. I don't think I need this. So this one pointing to node.right, and then node.right pointing to node.left. So node.right equals node.left, and then node.left equals none. And I'm going to return last right. So we can call helper on the root, and that's it. Let's see. Feels right to me, but I'm gonna have to. Oh, let's see if this one works. None type has nothing. Ooh. Oh yeah, the last right is going to be, because I'll keep calling. Okay, so that means this situation will never happen. So the node, well actually we should still do this, but we shall not call that. We should say if node.left, then we try to find it. If not, else, so it'll be like this. Last left equals this, if, else, node.left. If node.right, else node.right. And then, okay, let's try this. None type. If node.left, so I call it. If node.right, I call it. Otherwise, it's just. Oh, it's not. It's node. Yeah, it's not. Why would I do that? Try this. Okay, it's not. So I got 1, 2, 3, 4, and 5. What happened to 6? Okay, so when we call this, right? So this one, if node.left is nothing, so last left is this. And then I'll call node.right. And this is node.right. And then left or right, so it's by itself. Maybe that should be the case. Hold on. Okay, so left, so this dot right equals node dot right, and node dot right equals node dot right, and then return last is return this. So here 5, last right is this, and we say the last left is by itself, dot right equals node dot right. It's the same, and node dot right equals node dot left. Ah, that's where it happens. Okay, so last left dot right equals node dot right. Okay, and node dot right. We say if node dot left. That's the head, right? We should say if node dot left. Then we do this, and we set it to none. Okay, let's try this. A little bit trial and error, honestly. Not true. This one. Still not right. Last left dot right equals no dot right. Interesting. It doesn't make any sense because I said if no dot left, I do it. Otherwise, it's just going to be node, right? So this one shall always have something. Unless the last right is a none. But it shouldn't be, because last right equals this. We say if I have a right, then I'll go for it. Otherwise, if I don't have a right, then I'll just return node. Very interesting. Maybe we can, I don't know, like leaf node we can just return by itself. And then last left, it will be by itself, right? Dot right equals node dot right. That just doesn't do anything. And if node dot left, if I don't have a node dot left, I don't do any assignment. Let's see if this one works. That's just 1, 2, 3. So we have 1, 2, 5, 3, 4. Huh. This one also doesn't work. How about 1, 2, 5? That's as simple as it can get. 1, 2, 5 doesn't work. Okay, that's a serious problem. So we have 1, and then I go column left, so I have a 2. And from 2, if the left no, so last left is 2. Last right is also 2. And this dot right. Okay, last left dot right equals node dot right. Which is both a none. If no dot nothing. Oh, I didn't return. I didn't return here. That's very embarrassing, huh? I forgot to return. Alright, I have to wait. Okay, this looks more promising. Want to do another? Yeah, okay. I'm too lazy to do another one. Let's try this. Oh, we got a wrong answer. Shoot. So, what wrong answer we have? 1, 2, no, 3. Oh, I was afraid. I was about to try this. Okay, 1, 2, no, 3. One, two, three, like this. Okay. So last left, we're calling left, we're calling left. So this will return by itself. So for 2, the last left is a 3, and the last right is itself. So we say last left dot right equals no dot right. Okay, which is nothing. And if no dot left, yes, then no dot right equals no dot left, no dot right equals no dot left. So we'll put it here, no left, so it'll be like this. And then we return last right. We return last right. Last right is this. Ah. So if we don't have right, if it's like this, and my right tree is empty. If my right tree is empty, then the last right shall be the last left. Okay, so if we have, right, else it should be last left. Okay, so I just change here to last left. Okay, let's run everything else. Okay, this one shall be right. All right, so we have a little bump. Not what we had expected, but it turned out pretty okay. Right, it's okay. 114. Should be ON. Now it's tricky, right? So we traverse left to find the last node in a flattened left subtree. Here, if there is no left subtree, the last node on the left should be the current node. Then we traverse right to find the last node on a flattened right subtree. Very importantly, if there is no right subtree, the last node on the right should be the same as the last node on the left. Then we move the nodes around, current node, and we are done. So that's basically what it is. Okay, so this is today's solution. 225 test case. Same. Morrison traversal. So we go all the way to find a tail. And then tail.right equals now.right. That is correct. So okay, we'll go to the left subtree, and then we go all the way down on the right to find the tail. Once we find the tail, we say now tail.right equals now.right. So we're pointing there. That's cool. And now right, because now.right is already getting pointed. So now.right pointing to head. Now.right pointing to head. Okay, so this one points to head. And now.left equals none. Okay? And now equals now.right, because now.right is pointing to the head. So now goes to the head. So basically at each level, we go, so this is now, we put the head on the left node. We search all the way to the end, and then we connect the end to the right, and connect this here, and connect now.right, connect this one here, and then we move now.right equals head. So we move on to the head, so now becomes the head. And then we'll find its left, and then go all the way to the right. So with a new tail, of the left subtree. And now, alright, so every time we move to the left subtree, okay, every time we move to the left subtree, we located the head, yes, and we locate the tail. So we have head and tail. So move tail up to make tail in the right position. And then we move down. But once we hit the most, because all the now.right equals head, now.right equals head. Eventually, when we go to the last on the left, its right equals, so we will go out. And if it's not, oh, how is it even possible? I mean, I can see how this one works, but lordy, I'll never be able to figure it out myself. I'll be happy just with recursion. What's this solution then? Here, this one is the same. Oh. Next head, next tail. Well, I think I did better than last time. I think this one is easier to understand, right? the last left and the last right, and then we do something, but it does require a little bit more debugging to this one to be right. I mean, Morrison traversal, jeez. Yeah, the ingenuity that required to come up with this is marvelous. Yeah, think about it. Like, how do we do this? When we go to the left tree, that must be the head, right? That must be the head. And if we find the tail, then we can do this, right? We can do this. And then we keep on moving to the next head, because I know the current head, so the next head must be on the left side. So we'll go on to the next head. And then we do the same thing. And it works because as we do the same thing, we find the tail of that. And that tail will be pointing. So like the tail is always pointing to the same. So on the right, every time we move right, we always move to the correct node. And every time we move to the left, we are guaranteed. So basically this one has two guarantees. The first is every time we move left, and if it exists, it's always going to be the head of the flattened left subtree, right? So every time we go there, it's right. We're on the right track. And every time we do this, we'll always find the tail of the left subtree by going all the way down to the right. And once we find the tail, we make the correct connection between this tail to the next one. So that's also correct. That means if we keep going left, okay, we keep going left, keep going left, keep going left, then eventually we will finish traversal the entirety of the left subtree, right? And when we finish, we will end up on the last node of the left subtree. And when we do a dot right call, we will be connected to the next one. So that will be correct as well. So this is kind of the general idea. They make sure that these two are always right. We always go to the head, we always find the tail, and we always make sure the tail dot right is pointing to the right node, the correct node. And once we do that, then we need to do this. This is just the right now, because I say the left node is the head of the next subtree. Therefore, myself, my dot right, need to point to that head, right? Because I want to follow this trajectory. This is just basically following the trajectory, and I turn myself left to none. And if we don't have null dot left, right, then we just keep going right, keep going right, keep going right. This is a marvelous, marvelous solution. I cannot overemphasize how smart this one is. Morrison traversal. Man, this is impressive. So what is Morrison traversal? I think it's just to link your right node, the right child, to the next thing. Yes, that's the Morrison traversal, right? So you link the right to the right subtree. So once you do that, you don't have to, so it's basically this step, right? You go left, and then you keep going right to the last right, and you make the tail dot right equals null dot right. So once you visit your tail, if you go to pre-order, right? So root left, right. So at the end, you will visit right, but you don't have to unwind the stack to go to the root to go to the right side. You can just call dot right to go there. Yes, that is basically Morrison traversal. Yeah, I kind of want to practice this. Reading is one thing, writing it out is another thing. So this is a solution from a year ago using Morrison traversal. traversal. Now the key, the essence of Morrison traversal is that we link the rightmost node of a left subtree. We link the right child of the rightmost node of a left subtree to the right child of the root. This way, when we finish traversing the left subtree, we don't have to unwind the stack to go back to the root. Instead, we can simply call the right child of the rightmost node to go for the right child of the root. That is the Morrison traversal. So here is the deal. We say I call node equal to root. Okay. So we say while node, we say left. So it should be next head. Head, it is head. Head of left subtree equals node.left, right? So if head, then we say tail of left subtree equals head dot right, and we say while tail equals tail dot right. So we go all the way to the right. So at here, so we get, so find the rightmost node, and then tail dot right equals node dot right. So this is the Morrison link. Okay, so after we've done this, right, we make this connection. Then we need to make some moves because this is the tail, right? So we have the left subtree's tail. Tail dot right equals node dot right. We just make this connection. This connection is definitely we need to make. And then we need to make is node dot right, right? Node dot right, because I can know that I have to pointing to the head left subtree, right? So this one has to point in here, right? Now once we finish this, node dot right, pointing here, okay? And then node dot left, null it, because we have the left. And then we always say node equals node dot right, because the node dot right pointing to this. So we just basically go to the next node. And then we just keep going, and then that's it. Oh. Oh, I think it should be dot right. While this one dot right. Huh? Oh, I think I write it wrong. Alright, that's just too much. I want to remove all these. And we can just call this as the head of the left subtree. And if head, tail equals this. And while tail and tail dot right. Tail equals tail dot right. What if there's no tail? I don't remember doing this check on the other solution though. We got tail equals head. How about that? Because the head is if. We know the head must exist. Let's try this. Oh, what happened? Well, in this case, because I know head must exist, so tail dot right must exist, and tail equals tail dot right. Blah blah blah, tail dot right. So the tail shall be the last right, and then tail dot right shall equals node dot right. That's the Morse link. Tail dot right equals node dot right. Okay, and then what's not node dot right? It's head dot net. Wait, no, it is node. It is node. What are you talking about? It is node. Node is the parent. Node dot right. So tail dot right, node dot right, and node dot right will equal to head, because head is the left, and the node dot left cancel, and then node equals node dot right. Why is this not right? I feel like I follow the same. Thing. Yeah, no, it's not right. Oh, it is. And how come earlier it will fail? I just say while tail and tail dot right. Not sure. Don't want to know. I just want to try the last one. That's the Morrison. Yeah, we don't have to record the time because the time looks really bad. Okay, so that's that. Let's do an easy one. Relax. A zero-indexed num of length n consists of digits. If for every index I in the range 0 to n, digit I occurs num I times in num, otherwise return false. Hold on. If for every index I in the range, the digit I, digit 0, right? I occurs num this number of times. So num0, digit 0 occurs once. So 1 occurs 2 times. 2 is 1. Digit 2 occurs 1 time. 3 occurs 0 times. Okay. So basically what we want to find is the index, right? Index, and we use that's the number of times this index occurs. So we have to do a counter. Actually, I'm not sure. It's str. I think I should be fine. And then we say for I, dig in enumerate num, right? We shall say counter stri equals int dig, and we shall return all of them, right? All of this. That's what it's asking, right? That's, yeah. All right, I'll call today a day. Yeah, see you guys tomorrow. Adios.